snow day, school might be canceled. We can.
I love one.
This is the last lecture of the semester. And well, there's always things. Anyway, very good. Yes, sorry. Last. And there won't be a problem session on tomorrow. And so we'll get on the home stretch. Hopefully, and some great progress on your final projects. All right, so last time we had finished the derivation of the story of spontaneous emission using the Wigner-Weisskopf theory. Wigner-Weisskopf theory is an example of how one can derive this kind of irreversible decay sort of from first principles under the appropriate set of approximations. And it falls under the broader class of thinking about something we'll talk about in much more detail next semester, the idea of Markovian noise and the master equation, things that we've seen pieces of this semester that will sort of draw together more next time.
Does this theory still fall under the umbrella of the James-Cunning model?
No.
No, it
So
doesn't.
the James-Cummings model is specifically the model of a two-level atom or two-level system coupled to one mode of the electromagnetic field. What's completely different about this is that the atom is coupled to an uncountably infinite continuum of modes. And that changes the story completely. Because when we had the one mode, we kept track of everything, and we had this oscillatory energy went back and forth between the atom and the cavity in a regular, irreversible motion, and very simple oscillatory motion. They were just two coupled oscillators, basically. Whereas here we have something completely different, right? We have this irreversible decay of the system. And based on that, and which was, again, I'll just sort of remind you here, because we're going to revisit this again next semester. The whole story and how we were able to get out of this kind of behavior was because of the separation of timescales, because there was two very different timescales that come from what's called the Born-Markov approximation. It's called the Born approximation in a kind of arcane way because the Born approximation and scattering is a kind of, but it's really perturbative that there's a weak interaction between the system and the environment. So that means that there's a slow time scale over which the system changes because it's very weakly coupled to the environment. But the environment relaxes very fast through its equilibrium because it has tons of degrees of freedom. And the separation of those time scales allowed us to get here, okay? And so what we see is that the probability amplitude, initially was 1, and the probability to be in the excited state then decays with the rate gamma here, and gamma, when we plug it all in, has this form. This is what's known as the Einstein A coefficient. Because Einstein actually derived this first in a completely different way. I'll mention a little bit about in a moment, based on thermodynamic arguments, okay? But we derived it here from first principles, okay? Right. This should be omega cubed, excuse me. Right, and the other thing that we get out of the Wigner-Weisskopf theory is a sort of a piece of an approximation to the land shift. So as we discussed, when the system, in this case the atom, is interacting with the quantized field, one of the other effects will be to change what the energy eigenvectors are, to change what the energy levels are. The energy levels are shifted because they're perturbed by their interaction. In this case, that perturbation is the ever-present vacuum fluctuations. And so that comes out of the Wigner-Weiss spectrum. That's not the full theory because we made all kinds of other approximations which aren't fully valid when thinking about the level shift, because that's a very non-resonant effect, whereas the spontaneity is very resonant effect. And so it's a very excellent approximation to the actual line width, okay, or the spontaneous emission rate. All right, so, as I was saying at the end of last lecture, when we think about this, one of the ways we often talk about spontaneous emission is in contrast to stimulated emission. And we talked about this a little bit earlier in the semester when we were talking about driving atoms with laser fields and the absorption and Rabi oscillations, and the difference in the description that we sometimes learn about in modern physics, 100-year plus old physics, in terms of the way in which, historically, of course, in the early 20th century, people were trying to understand the spectra of light that was emitted from matter, from atoms, and astrophysical observations and otherwise, and trying to make sense of it from the point of view of radiation theory. And it didn't make sense. Of course, that's how the Bohr atom was born, to try to make sense of that. So the picture that was given and how we thought, thought about how light is emitted or absorbed from matter was in terms of quantum jumps between energy levels, right? And so you might have some energy levels, say in the side state and the ground state, and there were quantum jumps. That quantum jump could be what we call spontaneous emission. The atom will spontaneously jump from that, and in the process emit a photon whose energy, h bar omega, is equal to the energy difference. But also, could be absorbed. So if there's light around, it could be absorbed, and there'd be some rate of absorption. And in addition, what Einstein showed he actually first showed there has to also be an emission that was called stimulated emission, that if there is light present at that frequency, it will drive the transition down that way, okay? So there's a spontaneous emission rate, the rate that Einstein called, this is what he called A, and then there's a rate of, I'll call it stimulated, which is stimulated, it's an equal rate for either absorption or emission, and this would be proportional to how much energy there was around, energy density around at that frequency, okay? So this stimulated, Einstein said, was the B coefficient times the energy density at that frequency. So U is the energy, the spectral energy density. Okay, and the spectral energy density is, what, if you remember from the Planck theory and Rayleigh jeans and all of that, is the energy per unit volume per unit frequency. Okay, so if I integrate this over a certain frequency interval, I'll get the energy density in that, okay? And so what Einstein, how he derived the Einstein A and B coefficients was, said, suppose that this were a black body. So the atom were bathed in electromagnetic radiation that was at some thermal temperature B. So if I have a black body, then Planck's theory told us what the spectral energy density is, right? And we could write that if we wanted as the thermal number of photons. So the spectral energy density thus is equal to the the Planck this is the mean number of thermal photons, right, at that frequency, times h bar omega per unit volume if I'm in a volume, and then times the density of states. Okay, so this is the density of states. And this, unlike that density of states, was the density of states into a particular solid angle, which is what we calculate. This is density states in 4 pi steradians. And in a black body, this quantity thus, so we had in a particular solid angle, we had that this was equal to V over 2 pi cubed times omega squared over c cubed. That's what we had derived. Now I have to say, oh, it's in 4 pi steradians, and black body radiation is unpolarized, so for a given frequency, there's only going to be one photon, one of the polarizations that is along the direction of the dipole. So I have to divide that by 3 dimensions, and then I have 2 polarizations. So this is the general density states. It's the thing I'm sure you've done in your statistical physics, thermodynamics. Okay, so right. So from that, Einstein derived the A and B coefficients, but we can revisit that right now from the point of view of just thinking about Fermi's golden rule. Okay, so Fermi's golden rule is what's kind of up there already. It came out, the Wigner-Weisskopf theory is basically the same calculation that you've probably done in the derivation of Fermi's golden rule. It's just a little bit different in that we don't look at the very short time. We have exponential decay rather than a linear change in the amplitude. So if you go back and you look at your notes somewhere, or maybe you'll take it next semester, you'll see that, and you say, oh yeah, Deutsch said that was just like Wigner-Weisskopf, and you'll remember that. Okay. By the way, I call myself Deutsch in my own head, so. All right, so, right, so let's just do that, and I want to then talk a little bit more about spontaneous emission versus stimulated. So let's think about the rate of stimulated emission from the point of view of Fermi's golden rule. Whether I'm talking about absorption or emission, it's the same thing. So Fermi's golden rule says that this is equal to 2 pi over, if I'm going to write in terms of density space and frequency, it's 2 pi over h bar squared. The matrix element, let's say for emission, going from the excited state, there's some interaction Hamiltonian, the matrix element squared times the density of states at the frequency. Okay, that's what Fermi's golden rule tells us what the rate of emission is. Okay, and our interaction Hamiltonian over here now is the interaction. I want to think about this as the interaction with the black body radiation. Okay, it's not. I'm not thinking about this as the interaction with the vacuum fluctuations. We'll come back to that in a moment. So this is equal to minus the dipole operator dotted into the electric field at the positive frequency component or negative frequency component, if I'm thinking about emission, at the position of And, right. So actually, I'm gonna put, I think this 1/3 on here because it comes in, that 1/3 comes in over here when we think about that fact.
You said this is the interaction Hamiltonian with the black body radiation?
That's right.
Even though this Hamiltonian is describing the black body?
This Hamiltonian is describing the interaction of the atomic dipole,
Which is
the atom.
Yeah.
That's the atom. The black body is the field,
Oh, I see.
right? The black body is the field. So a black body, black body radiation is what I really mean, right? So you remember, black body radiation is the radiation in thermal equilibrium when I have a cavity at some temperature, right? So this is the electric field associated with the black body, okay? It's of course a statistical thing, but that comes into the density of states. Yes?
Is our field not quantized?
Our field is not quantized. We could quantize it, and we certainly could do exactly the same thing that we did before if we took this initial state of the field to not be the vacuum, but the quantum thermal state that we've discussed. And we get exactly the same answer, okay? But we're not gonna do that. But thank you for that question, it's good to keep that in mind. Okay, so what I was gonna say then is that this guy, the square of this matrix element then, because the black body is unpolarized, there's only 1/3 of it that's along the direction of this. So this is equal to the square of the dipole matrix element, which is d dot E, over 3 times the square of this field for a black body. Oops. Okay. And the energy density, yeah.
Should it be GE, not EG? Because that's what your are.
Yeah, it's true. I'm sorry, you're absolutely right, but the square of the matrix element doesn't matter. But you're right. I'll try to be more consistent. Doesn't really matter, because this is the square of the matrix element. If it's EG, it's the square of it. Right. So what I was going to say, we'll remind ourselves that the energy density. This is the positive or negative frequency component. The energy density, classically, is equal to time average. It's the positive frequency component squared over 2 pi times the density of states. Okay, why is it 2 pi rather than 8 pi? Because you may remember it's over 8 pi. It's because the positive or negative frequency component is twice the real part. And that factor of 2 is where that isn't there, okay? Okay, so when all is said and done, and you put all of that together, you get the following for the stimulated emission rate. It's equal to 4 pi squared over h bar squared, the dipole matrix element squared, times the energy density, spectral energy density. This is the Einstein B coefficient. And if I put all that together with what we just said over there, this is equal to 4 over 3 h bar. So I'm going to put in the energy density, I'm going to put in this form for the spectral energy density into here. And what I get is this is equal to this. Okay, so from Fermi's golden rule, what we get is this is the stimulated emission rate, this is the Einstein peak coefficient, and if I express the spectral energy density in terms of the number of thermal photons, I get this expression when I do all the math. Versus this. So what's the difference between the Einstein A coefficient and the stimulated emission rate? It's just, so what we find is that the A coefficient, or the spontaneous emission rate, is equal to the stimulated emission rate when n bar is equal to 1. Okay? And so often it is said that spontaneous emission is stimulated emission by one vacuum photon. Now, there are a lot of things that are kind of not correct about that. It's numerology, it's equivalent. It's kind of coming from the commutator of A and A dagger, which is where that extra 1 comes from. If you actually were to do what Nate suggested and quantize the field and put it in, we'd see that commutator come out. We'd say, oh, that commutator was a vacuum effect. But maybe even before I get to that, I want to just emphasize a few different things about what's going on here compared to what we described when we talked about a laser interacting with the atom, okay? When we talked about the laser interacting with the atom, what we talked about were the Bloch equations, the optical Bloch equations, and how the Bloch vector Rabi oscillated, which was a representation of the density operator, and the density operator rotated on, for if we had no spontaneous emission, it just rotated on the Bloch sphere, right? But if we had spontaneous emission, then you remember we had a mixed state and it went inside the Bloch sphere, and then ultimately came to some steady state. Okay. Now, once the steady state is happening, that's kind of the picture of this, which is detailed balance. So the way that Einstein solved this problem, he said there has to be detailed balance in thermal equilibrium such that the probability of the excited state is equal to this energy difference over K Boltzmann T, right? That's the thermal equilibrium. In order to have that thermal equilibrium, there had to be a detailed balance of things coming in and out. So the rate equation version of this is valid once the coherences have reached their steady state, okay? Because in this picture, we're not even talking about coherences. We're just talking about population jumping from here to here. Where the heck is the coherence that we said had to drive evolution? It's worth revisiting that again. Go back to our notes where we looked at this and think about the difference of the picture of jumping between levels versus the picture of the evolving master equation, okay? Okay, so but with that said, I would say, well, what can we say about this stimulated emission business? Well, in some sense, it's true that we could say that spontaneous emission is stimulated by vacuum fluctuations. Without the vacuum, the excited state would be a stationary state, and it wouldn't change as time. We need there to be coupling to the vacuum. But the physical role of the vacuum fluctuations is actually incredibly subtle. And this is something we started to talk about at the end of last section. I want to now visit it a little bit more detail, which is the classical theory of damping by radiation reaction. Okay. So maybe I'll just begin, and before I do this, let's do an aside. Let's go back to quantum. Let's say at time equals 0, instead of having the atom in the excited state, suppose I had some superposition of excited and ground state. Okay, so the atom is in a superposition of with some fraction of its amplitude in the excited state and some amplitude in the ground state. Okay? I'm not driving it now. It's just sitting there in the vacuum. And if I wanted to think about the state of the atom having forgotten about the field, of course, what's going to happen? If I were to look at the density operating for this system, well, maybe I'll look at the following thing. Let's say I ask, what is the dipole moment of this atom at time t equals 0? Well, that's going to be equal to this expectation value. I only have the off-diagonal elements here, C, E, G times G plus C E star, G star, E, D. Right? When I take the expectation value, I only keep the off-diagonal elements because the dipole operator doesn't have, right? So this is my coherence in the system at time t equals 0, and this is the complex conjugate of it. Okay, this is VEG, or GB. What happens at a later time? Well, we know what's going to happen is, as we discussed when we talked about T1 and T2 times, there's going to be decay of both population and coherences as this atom spontaneously emits. And I can write down because if I'm interested I want to know how is the dipole evolving as a function of time, the electric dipole of this system. So I've started the system polarized in some way. To the degree to which this is non-zero, there's going to be some initial dipole, because I've pulled the electron away, I've made a superposition of the grounding size. And I want to know, how does the dipole change as a function of time? It only depends, this thing at a later time is going to depend on the time dependence of the off-diagonal elements. And since I'm not interested in the populations, I don't have to worry about the refeeding term. You remember, I can treat the system, if I'm interested in things that just depend on the population, the excited state, or the coherences, with a non-Hermitian Hamiltonian, with an imaginary part, as we studied earlier in the semester. So I can write this at a later time, unnormalized, in terms of the so-called effective Hamiltonian, which has an imaginary part to it. And that will mean, I'm not going to include the refeeding term, but there's a phase that comes from whatever the ground state is, plus the excited state, and I'll put an imaginary part into the energy eigenstate that is related to the spontaneous emission rate. You remember that? So with that, this is a perfectly good description for me to calculate this. And what do I find? What I'll find is that this is equal to the real part, because this is equal to the complex conjugate of that, of the matrix element times whatever the initial coherence was, e to the minus I omega e g t minus gamma over 2t. And that can come outside because that's real. Okay. So, what do we see in this problem? What we see is that the dipole will oscillate. It'll oscillate at the resonance frequency, and the dipole will decay. So if I look at the mean dipole moment as a function of time, what I would see is something like that. Okay? So the dipole moment would decay, and eventually at 0 time there'd be 0 dipole moment because all of the population would go to the ground state, and in the ground state there is no dipole moment. Okay? So that, yes sir?
Wait, sorry, how did you get the effective Hamiltonian there? Like what is the reason?
So I will remind everybody that the effective Hamiltonian is the Hamiltonian of the atom. And then I added an imaginary part. Okay. So when a good description of this open quantum system in the same, it's perfectly valid, it's what comes out of the master equation. It's like in classical physics, I'm thinking about a harmonic oscillator, and I think about a charge on a spring, or a mass on a spring. I say the damping is an imaginary part, because that's how the energy damps. So this is the description that we had phenomenologically when I just put in T1 and T2 terms. But it's actually exactly the same as you get from the master equation. This is not the full description because this is not normalized. This is not Hermitian. Because this is ignoring the refeeding into the ground state. And that refeeding term we cannot get with the deterministic evolution. We'll talk about that next semester. That's a quantum jump. There will have to be a stochastic random process that causes that jump. However, it doesn't matter for this calculation because the off-diagonal elements don't depend on that. So this is a perfectly valid description. Very good. All right, so that's what we see, but let's now think about the classical thing. And we were talking about this at the end of last lecture, which I said, now I'm gonna have the Lorentz oscillator model. Where I think about an electron bound to the nucleus as with harmonic oscillator. It has some resonance frequency and there's some mass of the electron, okay? And now when I think about the dipole associated with the displacement of this thing, okay? And phenomenologically, what happens? I pull the electron away from equilibrium, and the mass is going to oscillate. And let's assume this is a frictionless spring. There's no other friction in the system. Then, and I look at the, so here the dipole is the charge times the displacement. Okay. So if I look at the dipole as a function of time, the magnitude of that dipole moment as a function of time, what's it going to do? Exactly the same thing, classically. The dipole oscillation will decay exponentially, some classical decay rate. Why does it decay?
It's radiation.
Because it radiates. An oscillating dipole radiates. It radiates in a dipole pattern, but whatever. There are electromagnetic waves, there are spherical waves that propagate out, and they carry energy. And since they carry energy, that energy must have come from somewhere, and it comes from the mechanical motion of the particle, and thus the particle its motion must be damped, okay? Now, the description of that in classical electrodynamics is actually very fraught, because this damping is what's called radiation reaction, and some of us studied it a little bit together last semester. Whereby we can think about this, I mean, if there is a force that's causing the electron to change, it must be coming from, other than the force of the binding, that's one force, but if there's anything else that's changing it, where's that force coming from? Well, it must come from the field itself. The self-field must act back. That's why it's called radiation reaction. And that has all kinds of singularities and problems associated with it, okay? They were mostly solved by when we put quantum field theory, and there are other singularities come in that we just can't get rid of, but basically the quantum theory kind of solved this problem. Nonetheless, we can get a lot out just thinking about energy conservation in this problem, okay? So let's just say the following thing. Again, let's suppose that this is a weak interaction, so that this is much, much weaker than the binding, and thus much smaller than omega naught. Let's assume that we're radiating at that rate. Oh, before I do that, I guess I should remind ourselves, what is the rate at which a dipole emits energy? What's the power radiated by an oscillating dipole? Some factors there. So first, let me ask you to remember the following thing. A oscillating dipole, or this oscillating mass, is accelerating, okay? So how does the power depend on the acceleration? Because accelerating charges radiate. They're moving at constant velocity, they don't radiate. It's because it's oscillating, it's accelerating. So there's the Larmor formula. Which says that the power, which is proportional to the square of the electric field that's radiated, is proportional to what? In terms of the acceleration. I know, how soon we forget. The field is proportional to the acceleration. So the power is proportional to the acceleration squared. Okay? So that's the acceleration. That's x double dot. Okay? All right. So if I have an oscillating mass and it's oscillating at frequency omega naught, at what rate is it accelerating? If it's x double dot.
Squared.
Omega naught squared, right? Then squared. So the power radiated is proportional to omega naught to the fourth power. Okay?
Yeah.
Because the acceleration is proportional to the square, and that's then correct. So the power is related to omega to the fourth. Okay? Now let me get all the factors here. When you've done this problem, if you've done it in E&M, those of you who were in my class this semester, we did it. And what we find is that the power radiated is for a radiating dipole is equal to omega to the fourth times the square. So what I have, I have a dipole that as a function of time is, has some amplitude and it's oscillating with some frequency omega naught, then this is the square of the dipole magnitude omega to the fourth over 3 c cubed. Okay, so that's in CGS units. All right, so now what I want to calculate is this classical rate of damping, just from energy conservation. Okay, so we're going to say, make a little ansatz and say at the displacement now has an initial amplitude A. It would oscillate in the absence of damping, just like cosine omega t. But I'm going to put in an amplitude damping factor. The power will, the energy will damp at twice that. Okay. So now I want to know. Okay, this is really the time average, if we remember that from, because instantaneously it's everything is oscillating frequency average. I want to know what is the time average energy in the harmonic oscillator. Time average over an oscillation. Well, that's the time average of the kinetic energy plus potential energy. And if you remember a harmonic oscillator, they're equal. The time average is equal. And if this is much smaller than that, then I don't have the time average. This factor is basically constant over the time scale that I'm time averaging, because I'm assuming this to be true. Then this is equal to 1/2 m omega naught squared amplitude squared e to the minus gamma t. And so the rate of change of this, or time average over a period, is equal to minus gamma times this. But this has got to be equal to the power that's radiated. So what's the power that's radiated? It's here. So this is decreasing minus the power radiated times e to the minus gamma t. And the power radiated we have over here is omega naught squared c cubed, and the amp we have initially a dipole that's displaced by amplitude A. Okay? So, putting that all together, I get gamma times 1/2 m omega naught squared A squared. The e to the minus omega, e to the minus gamma t cancels. Omega naught, omega naught to the fourth. Pardon me. Omega naught to the fourth over c, 3c cubed times the electric field squared. All right, times a squared. The a squareds cancel. And so what I then get, let's see. These factors are, make sure I got this right. Yeah, oh, I did. Okay, good. So this tells me that gamma classical is equal to 2 e squared omega naught squared over 3 mc cubed. Okay. Or I could write this as 2/3 e squared over mc squared omega naught over c squared. Okay. So classically, we get, this is the rate at which the electron in the Lorentz oscillator model will decay. This, did I have all
Should
the
only the omega not be squared, not the c?
Right, 'cause now
yeah,
it's supposed to
hold on a second, let me make sure. Right, omega naught over c cubed.
Wait, that's more confusing.
Omega naught squared over c.
That works.
Yeah, but I want to check the units, okay? You must check the units, otherwise you don't know whether you've done anything that it says. Does this have the right units? Gamma is a rate, has the units of 1 over time, okay? This has the units of 1 over length squared. This has the units of length over time. Do I know why it's supposed to see it? Okay. What is this? Well, mc squared has units of energy. But in God's units, also known as the units I prefer, the charge squared over a distance is a potential. That's the electrostatic potential. So this has the units of energy, right? So that means this thing, E squared, is an energy times the length, and the mc squared, as Einstein taught us, is energy. So, yay! This is right. This has the units of 1 over time. Phew. Okay, so this whole thing is known as, because this has units of a length, this thing is called the classical electron radius. It's called the classical electron radius because it's the radius that the electron would have if its mass times c squared was the electrostatic energy of concentrating a ball of charge into the radius of the electron and say, so Lorentz said, oh, Einstein, yo, Al, the mass of the electron is coming from its electrostatic energy, and that's what we call it. Now, this is not the radius of the electron, it's numerology, once again, but nonetheless. So what we have, yeah, so this thing is equal to tri c 2/3 omega naught squared over c times the classical electron radius. Now, okay, how does this compare to the Einstein A coefficient? So let's look at the ratio of these guys. The Einstein A coefficient is 4/3 over h bar, the dipole matrix element, which is E times the position of the electron squared, omega Eg cubed over c cubed, divided by 2/3 E squared over mc cubed times the frequency, the resonance frequency squared. So when you put all that together and you cancel all the factors, this is the charge of the electron, this is the excited state, sorry, E means two very different things. Over here, this is equal to the matrix element of the position of the electron squared divided by h bar over 2 MEG. Okay? This thing is known as the oscillator strength. Why is it called the oscillator? Well, when Lorentz and Lorentz oscillator model was proposed to try to explain the spectra of atoms, and they used the charge of the electron, it didn't work. And they had to put in a fudge factor, and they just introduced, they said, oh, there's an oscillator strength, there's some oscillator strength. And that oscillator strength, at the end of the day, comes from quantum mechanics, because it's not really, so what, this thing is the quantum mechanical matrix element of the relative position of the electron to the nucleus, right? That's what this matrix, what is this in the, do you recognize that factor? Does it look familiar in any way? Yeah, this is the 0 point energy of a harmonic oscillator. I can't, it's numerology, but this is saying there's something different about a harmonic oscillator, which is what you have in the Lorentz oscillator model versus the true relative position of the electron. Okay. So we can basically get, you know, a lot of the physics from the classical theory as long as we throw in an oscillator strength to the problem and just think about it as radiation reaction. I want to think about this even more going back to what we wrote here. Okay, let's now just revisit this picture that we had of the Larmor formula, which tells me what the power should be radiated for an oscillating dipole. But take the quantum mechanical oscillating dipole. Here's the quantum mechanical oscillating dipole. If I had an oscillate, which is an oscillating charge distribution, that's going to radiate. We can call that radiation spontaneous emission, or we just can call it radiation because the charge, the electron is going up and down, the center of its wave packet is moving relative to the nucleus, and thus it will radiate. The quantum mechanical theory says it will emit photons. But that's also true classically. So let's take this dipole expression and plug it into the Larmor formula and see what we get. Bless you. Alright. So let's see. So the power radiated is equal to, given that expression over there, we have, that's the, so we have omega Eg to the power 4 over 3c cubed. Then we have the magnitude of the dipole matrix element, which, because again, it's that plus its complex conjugate, is twice the real part. It's this times whatever the initial coherence is squared. Okay. So that's equal to 4/3 omega Eg to the power 4 over 3c cubed, the dipole matrix element squared, times the square of this initial coherence. Okay. But what is that power radiated? That power radiated in this problem is spontaneous emission. So the rate at which I will radiate is the Einstein A coefficient, and the amount of radiation I get is times, that's the power radiated. I'm radiating 1 photon per unit spontaneous emission rate. That's my power radiated, and of course, it depends on my initial coherence, because the amount I have radiate will be 0 if I didn't have any of that.
Can we assume that omega is omega Eg?
We can, because that's what we're emitting. Okay? So when, I'll call this omega Larmor. This is coming from the Larmor theory. It's just saying, I have a dipole, the dipole's oscillating. The oscillating dipole will radiate. It radiates at this rate. This is the power it radiates. Let's solve for this. What do we get? No, I had this twice, sorry. Yeah. Let's see, is it gone? It's gone. How does this compare to the Einstein A coefficient?
What happened to H bar?
Oh, yeah, H bar. Thank you.
Now, it's very simple.
What is it? It's the same thing, up to this factor. I mean, this factor is not there because actually what the vacuum does is induces, I mean, initially I have the system sitting on the north pole of the Bloch sphere where it had no dipole moment. And what's happening is the vacuum is causing this thing to fluctuate, and once it fluctuates, it will rotate at the free evolution, it'll be free evolution, and it will radiate and spiral down here. And that rate of radiation is the Larmor formula. Hold on 1 second. So the Larmor, the point I want to emphasize here is spontaneous emission is an oscillating dipole. That's the physics of it. Things radiate, the atom emits a photon because its dipole is oscillating. If it wasn't, it's that just because we describe it quantum mechanically, the whole physics of what we understood from radiation theory still follows. Yes, Ben?
So, as you were saying, this is sort of just a quantum mechanical description of just a radiating photon, and I don't see the part where we actually added in the bit that is vacuum fluctuations.
We didn't. Because this is not the same thing as the Einstein A coefficient. Because the Einstein A coefficient doesn't have this. What I did in this little calculation, I said, let's just check. If I were to look at, I said, I have a dipole that is oscillating as a function of time given from quantum mechanics, and plug that into the classical Larmor theory. What do I get? The answer is this, which is almost exactly what we got from Wigner-Weisskopf and all kinds of crazy nonsense with density of states and the Markov approximation and the like. And what I'm trying to argue is the physics is the same. We can't get it exact, right? Because it isn't exactly. The Einstein coefficient doesn't have this. But the physics of this is essentially the same. And so I don't really, well, I'm trying to think what I want to do in the last 15. Yes, please.
How do we get a dipole for a single state that's not superposition of different levels?
We can't.
Okay.
We don't. So these states, if I start, so this is what I was trying to argue, but I didn't do very well. If my initial state is this, there is no dipole moment. Okay, so that's not this problem, the problem where I started. However, it's very closely related. And so what is the role, one of the ways of thinking about the role of the vacuum is to induce a dipole. Okay, so in the absence of the interaction of the field, I know what this has been on the Bloch sphere. I start at the North Pole. I have no coherence and thus no dipole. But the vacuum fluctuation causes this thing to fluctuate. And once it fluctuates, you're off to the races, because then it will start processing, free processing, and it will start pre-processing at its, and that dipole will radiate. So one way to think about spontaneous emission, it's not that it's stimulating a quantum jump per se, it is it's stimulating an induced dipole, and that induced dipole radiates.
Coupling to the environment causes dipole.
Yeah, because the coupling of the matter to the field induces a dipole moment. It polarizes the atom in a fluctuating quantum way. Now this is a little bit loosey-goosey, right? I mean, and in the notes is a whole description, and there was a long debate before my time about what is the role of vacuum fluctuations versus what is the role of radiation reaction? To what degree, if I do this exactly quantum mechanically, rather than let's do half of the calculation quantum mechanically and half of the calculation classically. What if I did a fully quantum description of the system? And I can do it with the equations of motion of the atom and the electric field operator. I can do it in the Heisenberg picture. We solved Wigner-Weisskopf in the Schrödinger picture, where things are a bit obscured. But if I do it in the Heisenberg picture, it looks like Maxwell's equations. I have dynamics of the electric field operator, and you can see in that different components of what is the role of vacuum and what is the role of radiation. And the answer is both play a role. But I think it's important to understand physically that spontaneous emission is radiation in the same way. Yeah.
So in this description, it's not really, you can't really think of it as a jump then, it is like a coherent.
Yeah, well, that's an interesting point. So, it is a bit complicated. So, let me think about the following problem. I actually use that word. There it is. Let's say classically, I have a charge on a string. Okay. And let's suppose that I send in a plane wave on this system, which has some electric field, which will cause this thing to oscillate. Okay. So what will happen is that this thing will radiate. And when it radiates, some of the light goes off in another direction. Okay. This is called wave scattering. And the coherent oscillator will oscillate. And in fact, if this thing has some frequency, omega L, even if this has a resonance frequency, in steady state, this thing radiates. This is what's called elastic scattering. The frequency of the scattered light is the same. And it's a coherent process. I drive this oscillator, I make this thing jump up and down, and it radiates, and some of the light goes off in a different direction. Okay? That's the classical Lorentz oscillator model scattering. I want to compare that now to the picture of an electron bound to the nucleus in an atom, which has a ground state and excited state. There's a natural resonance frequency, which is omega EG. I'm going to shine my laser on this. Okay? And we know in our problem what that does is it's going to be detuning. There's going to be, a laser frequency, be a Rabi frequency associated with that. And it's going to cause this atom to undergo the same kind of motion that we just described a moment ago. It starts in the South Pole, it starts, going out doing something. And eventually, after some few gamma, this thing can radiate, it will come to some quasi-steady state. Now, when it's in steady state, in the rotating frame, it's there, but in the lab frame, it's rotating at the frequency omega EG. Okay? Now, photons are being emitted by this atom. When I shine, let's say I had one atom in a laser trap, in a tweezer, or an ion in an ion trap, and I were to shine laser light on it, it will fluoresce. you will see photons. You can collect those photons. When it's near resonance, this is called resonance fluorescence. This is a very important problem in quantum optics, and if I had more time, sometimes I get to it, sometimes I don't.
Correct.
What?
Fluorescent resonant energy transfer? Is that one of the things you end up getting to when you have time?
Well, I mean, there's various aspects of this. I mean, of course, there's heating and the motion of the atom, but that's not the problem I want to focus on in the moment. What I want to focus on is what is the nature of this light that is scattered from this atom, okay? And comes to Andy's question is, to what degree can I think about this as coherent versus quantum jumps? It's a very subtle point. So I'm going to ask a slightly different problem. I'll come back to this. Let's say I have two trapped ions. This experiment has been done, okay? They're trapped like this. And I'm going to shine a big fat laser beam into the board, right, which is going to have I'm going to, I have it into the board, and it causes these things to oscillate, okay? Or I'm going to, more generally what I'm saying, I'm going to shine it like this, and it's going to be off resonance by some amount, and it's going to fluoresce, okay? And now I'm going to look at the fluorescence on a screen. If these were two antennae that were, say, oscillating currents, what would I see on the screen here in terms of the intensity? I would see interference. I would see two-slit interference. What do I see for the two atoms? The answer is, it depends. It can be exactly the same. The question is whether I see elastic scattering or something which is more like random spontaneous emission, incoherent. And it depends on the saturation parameter. So when the saturation parameter, which we will remember is this, is much, much less than 1, then there's very little population in the excited state. The spontaneous emission is coming from whatever is in the excited state. And if I were to look at the spectrum of the light that is emitted from this, what I see is the following. There's going to be an elastic peak at the frequency at which I'm driving the system with this laser frequency. And in addition, there's going to be around resonance what's known as the Malo triplet. Which is inelastic. The elastic processes are ones where I absorb and emit the same frequency. The inelastic processes are one that involve multiphoton, they're nonlinear effects where I have multiphotons, and they are the spontaneous emission. So let me try to summarize what I'm trying to say. When we're driving the system with a laser that's coherence, I'm going to induce coherence in the atom, and that coherence will oscillate. That coherent wave packet will oscillate, and it will radiate. And it will radiate just like a classical wave does, and that wave is phase coherent relative to the drive such that you can see interference. But in addition to that, the atom is being kicked around by the randomness of the vacuum fluctuations. So in addition to that, there are these spontaneous jumps, which causes the dipole to fluctuate. And that fluctuations are completely random and correspond to another part of the spectrum. But how much of that randomness I see depends on how hard I'm driving the system. If I don't drive it very hard, such that I don't see much in the excited state, it's all elastic scattering. And I should just think about it like an antenna. I should think about it like I'm driving current. Yeah, and then Benny had a question too.
How come the random jigglings or whatever from vacuum fluctuations only show up in part of the spectrum instead of being across the entire spectrum?
Well, they have a certain spectral features that are determined by the resonance structure of the atom. So they occur depending on, if I were exactly on resonance, if I drove the system on resonance, it would look like this. This width here depends on gamma, and these side bands depend on omega. So there's various scales in the problem. There's the spontaneous emission rate, there is the resonance frequency, and the Rabi frequency. All of those play a role in the nature of the spectrum that we see, okay? We can understand these in terms of, fundamental processes of absorption and emission of photons. But a point that I sort of want to emphasize is that we shouldn't forget about the classical picture of radiation, even though there is an underlying quantum description that we can get at fundamental level. At the end of the day, the physics that we learn classically can still apply. And it can become incredibly confusing if you think about spontaneous emission solely as this quantum jump, when so much of what we see is really just really classical radiation theory as well. Yeah, Benny, do you have a...
You answered it by writing gamma as related to the line.
Yeah. Yes?
Should that be gamma squared?
It should be gamma squared over 4. Yeah. All right, I think we're going to conclude there. So let me just sort of think about tying up together what we've talked about this semester. As I said at the very beginning of the course, quantum optics, from my perspective, is the story of quantum coherence. And quantum coherence is, in some sense, the heart of quantum mechanics, the idea that events that we see and that we ascribe probability to their occurrence, we can only do so when we include the possibility of interference between different possible histories that can lead to those final outcomes. Okay. And quantum coherence can then make differences from what we see in the classical world. And we saw that in what we were talking about today in the context of emission and absorption of light by atoms, and the way in which we think about Rabi oscillations versus bound harmonic oscillators, and the quantum coherence associated with that process, and the quantum coherence that we saw in terms of wave interference, and the degree to which we can think about interference between waves classically in electromagnetic theory and versus the quantum theory in terms of probability amplitudes, and how we distinguish classical versus non-classical light, and then finally in terms of the process of interaction between the quantum light and the quantum atom. What are we going to do next semester? Well, next semester we want to think a little bit more hard about other non-classical features that we haven't really focused on this semester. Number one thing that we want to talk about, we talked about the idea of a statistical mixture of coherent states. And the Glauber-Sudarshan P representation. But the whole way in which we think about the field from a classical versus quantum perspective, to what degree, what's the right way to think about a probability distribution of wave amplitudes? It'll get us into the whole theory of quasi-probability distributions, and particularly the theory of the Wigner function, which is extremely important in understanding distinctions between quantum and classical. I might say it's the whole story. In addition, the thing that we've mentioned from time to time, but we haven't really talked about in great detail, is entanglement. Entanglement is another quite important quantum feature that is quite distinct. Some people say that might be the whole story. So we're going to talk about entanglement, and in particular, we're going to talk about how the different kinds of entanglement that we can create and measure in quantum optics. And then finally, we're going to put that story of entanglement and correlation is very intimately related to the theory of open quantum systems. And we'll spend about half of the semester, next semester, talking about the theory of open quantum systems and putting all of that. So pretty much most everything that we're going to do next semester, we've kind of already, most everything, we're going to talk about the Wigner function, but most everything. So I think just try a little bit to try to absorb what we did. We look back and think about these different pieces because we'll revisit them again next semester. All right, we'll call it conclusion from there. I also wanted to say, I encourage everybody to fill out the course evaluations. It's always helpful for me. You know, I've been doing this for a long time, but every time I teach, I learn something new. And it's always been great fun for me to do it, but it's also important for me to hear from you about things you'd like to see differently in the future. So I do encourage you to put that out. All right? Have a good one, everybody, and look forward to seeing your final projects, and have a good break if I don't see you.